Hello everyone, welcome back to the course on cryptography and network security. In this session, we'll be on continuing with the next substitution technique called Hill Cipher. In this session, we try to discuss on introduction and working principle of Hill Cipher encryption process with suitable example, and also with decryption process. At the end, we will conclude. In today's session, at the end, my students will be able to understand the concepts and working principles of the Hill Cipher. They are able to represent the plain text and the keys using the matrix notation. Then they will be applying matrix multiplication with modulo 26 for the encryption and computing the inverse key matrix for the decryption process. So finally, they will be able to apply encryption and decryption by making use of matrix multiplication in the case of Hill Cipher. Coming to the introduction to Hill Cipher is a classical symmetric encryption technique developed by Lester S. Hill in the year 1929. It is basically a polygraphic substitution cipher that encrypts the blocks of letters using matrix multiplication and modular arithmetic. Unlike any other simple substitution techniques, Hill Cipher processes the multiple letters at a time, which increases the security by hiding the single letter frequency patterns. So comes into the steps involved in Hill Cipher encryption. So whatever the plain text or the key which we are going to be using in the case of Hill Cipher, we have to be convert the letters into numbers. The standard mapping, all the alphabetical letters we are going to be assigned from 0 to 25. Then we are going to be dividing the plain text into blocks, and then we are going to be converting the key into 2 cross 2 matrix, and the plain text is divided into pairs of letters, and finally I'll be constructing the key matrix called 2 cross 2 matrix of numbers. When it comes to the steps, so we just go on performing the matrix multiplication. The ciphertext vector is going to be obtained by using the encryption formula called C equals P into K mod 26, where P is the plain text row vector and K is the matrix and C is going to be ciphertext vector. So before getting into the actual formula, we need to go on convert the numbers back to letters. So because we are going to be performing the matrix multiplication by using numbers, the results what you are going to get, that again we convert it back into letters to get back the ciphertext characters. So in this example, to understand how exactly the encryption process is involved, so here we are going to be considering the key is called help and the plain text we call it as fire. So by making use of the standard number mapping and all, we have to be gone map A to Z with 0 to 25 number. So here the plain text conversion is, so F is going to be identified with the positional value 5 and I is going to be identified with 8, R is 17, E is 4 in the standard mapping from 0 to 25. Then I'll be gone dividing that entire plain text into two blocks. So the first block is a pair of letters called Fi and the second plain text block is Re. So the values which I'm going to be representing in the row vector. Now the key is help. I'll be go on finding out the equivalent, the positional values for each character which is available in the help. So fire is going to be HELP, the value will be 7, 4, 11, 15. Sorry, here FIRE is not an FIRE, HELP. The key matrix becomes 7, 4, 11, 15. So when we go for encrypting the very first block Fi, so the plain text block is 5, 8. The formula we are going to be used to perform the matrix multiplication is P into K, that is the first block into the key matrix. 5 into 8, 7, 4, 11, 15 is the key matrix. So when I'm going to be performing with the first element and the second element, I'm able to get 123 and 140 is the value. So these two numbers are greater than 26, then I need to be go and apply the modulus 26. So 123 mod 26 is nothing but 19, and 140 modulus 26 I'm going to be get as remainder 10. So 19 and 10 I'm going to be converting back into the letters called T is the equivalent value of 19 and the K is the equivalent value is 10. So the very first cipher block for the plain text block is TK. Similarly, I'll be gone performing with a second block, that is RE. So RE is going to be get multiplied with the key matrix. So I'm going to be getting the two elements 163 and 128. Again I will be going to apply the modulus 26 in order to get back the values 7 and 14. So 7 and 14 is converting back into the alphabetical letters, that is equivalent to H and Y. So the second cipher block will become HY. So with this encryption process, I am able to get the entire cipher block for the plain text fire, that is TKHY. So this is how we are going to be performing the encryption operation. So now we move on to how we are going to be performing the decryption process. So basically, compared to decryption process, encryption process is simpler because we directly multiplying with a plain text with a key matrix. So when we come to the decryption process and all, the formula which we are going to be used is, so plain text P equals the cipher text block multiplies with inverse of the key matrix. So here the inverse of the key matrix we have to be obtained before performing the decryption process. So now again, so TKHY, whatever the cipher blocks are there, I'm going to be divided into C1 and C2. This is 1910 and 714. So now before getting into the actual finding out the key matrix, so K inverse is nothing but 1 over determinant of K into adjoint of K. So I will be gone finding out the determinant of K. So 7 cross 15 minus 4 cross 11. So 105 minus 44. 61 is the answer I'm going to be get. So again this number is greater than modulo 26. Then I'm going to be apply the modulus 26. So I'm going to be get as 9. So now in the step 3, so I wanted to find out, because the formula of K inverse is 1 over determinant of K. So 1 by 9. So I can't able to multiply 1 by 9 with adjoint of K. So I wanted to go and find out the inverse modular for the determinant of K. So that is nothing but 9 inverse mod 26. So I need to be go and get the remainder. So I need to be go and find out a value for this 9 inverse, that is nothing but 3 in this case. So now see here, so K inverse equals to determine inverse into adjoint of K mod. So I already find it out the inverse of the determinant, that is 3. That is 3 is going to be get multiplied with the adjoint of K. So the final answer I'm going to be get as 45, 66, 45, 21. So all these numbers are greater than 26. I'll be going to apply modulus 26 for all the 4 numbers. So I'm able to get back 19, 14, 19, 21. So finally the inverse matrix of the key K equals 19, 14, 19, 21. Now I need to be going to make use of this K inverse in order to get back our plain text. So very first cipher block I'm going to be performing it. So 1910 is multiplied with K inverse. The first value is 551 and the second value will be 476. So both the numbers are greater than 26. I'll apply the modular 26. I'm able to get back 5 and 8. So plain text numbers will be 5 and 8. I'll be converting into an equivalent letters. So it becomes Fi and the plain text block will become Fi. The very first plain text block we obtained back by applying the decryption process. So in order to get back the second block, so again the second cipher is multiplying with the K inverse. The first element value will be 589. The second element value will be 602. I'll be applying the modular 26. So I got 17 and 4. So I'm going to be converting the 17 and 4 into the equivalent letters called R and E. So finally the second block of the plain text we obtained as RE. So finally the blocks are obtained. That is, very first block is FI, that plain text block, and the second block will be RE. So our final plain text we got back by applying the decryption process. So now at the end of this session, so Hill Cipher, what and all we discussed. Hill Cipher encrypts the plain text using the matrix multiplication and the modular arithmetic. So we are going to be processing the block of characters. It hides the individual letter frequencies, provides the strong encryption than any other simple substitution techniques. The key matrix must be invertible, modular 26 to successfully decrypt the ciphertext. And at last, Hill Cipher provides the fundamental understanding of matrix-based cryptographic transformations used in modern encryption systems. So with this, we are ending the today's session. So we will come back with the next kind of technique in the next session. Thank you.